Okay, so let's think of a wave function a e to the I kx minus omega t, and maybe plot this kind of thing. Right, that's just this sinusoidal function that's traveling to the right because of the minus sign. So the wave number is just 2 pi over lambda, and of course the momentum p is h over lambda. So we see that for this traveling wave, there is a precise fixed wavelength, lambda, and that means that there's a precise or fixed momentum. So we only have one momentum corresponding to a particle represented by this function, and therefore we can say that the range in momentum for the particle is 0. It's a particle with a well-specified momentum. But where is the particle? Well, if we do psi modulo squared, we get the A modulus squared. That's just some positive number, and we know that means that the probability density is the same everywhere, and so the particle is not localizable, it's not physical, because the range of possible positions is infinite. So this is infinite. So to get a description of a physical particle, we need some kind of function that represents a localized wave. And so when we do that, what we need are many such waves with different wavelengths so that they can add together and cancel certain places and produce a localized disturbance. And to do that, therefore, if you need many, so let's say many lambda, so you have a range in lambda, that's not 0, and that corresponds to a range in momentum. So we can say that delta p is not equal to 0. And of course, we can see that delta x now is not infinite. We can say delta x is equal to finite. Okay, so this is not equal to 0, so this is also, we can say it's finite, and it's not infinite. So what we're concluding is that the wavelength to represent a physical particle is not unique, and therefore P is not unique. You need some range in momentum, and that ultimately P and X cannot be perfectly fixed, because if we fix P, then this is completely unspecified, and if we make this completely specified, then it turns out we need an infinite number of different wavelengths and momentum, and so we're getting at this relationship between delta, the range in position, and the range in momentum, that has to be greater than or equal to some number. And we'll see that. So the more we want to localize the particle, the greater the range of momentum, because to represent a more localized particle, we need a greater range in wavelength. So the uncertainty principle for particles stems directly from the fact that particles are represented by waves.